Hi everybody and welcome to session 14 of Phil 2002 Logic, How to Defeat Your Foes with Reasoning. In the previous session I introduced you to the basic tree rules for monadic predicate logic. So here the tree rules take all of our propositional logic tree rules and add to those tree rules some extra rules to handle the quantifiers and the negated quantifiers. So for the negated quantifiers, we just turn each of our negated quantifiers into the other quantifier and move the negation over. So those two rules are relatively straightforward. The unnegated quantifiers, however, have fairly specific rules to each of them, and they're both sort of quite different and important to understand. So for the existential rule, what we do is to get rid of the existential, we remove the variable that the existential has within its scope, and then we take our first unused name that appears on a branch in a tree, and we take our first unused name for a branch on a tree, and then we use that name instead of the variable throughout the proposition that the existential quantifies over. And for the universal claim, what we do is we take out the variable and then we substitute in any name that we like that appears in the tree. In order to complete trees in monadic predicate logic, it either has to be the case that every branch closes or that the tree is saturated. And a tree is saturated when, first of all, everything that can have a rule applied to it has had a rule applied to it. And second of all, the universal quantifier has had a rule applied to it at least once, and that the universal quantifier has had every name that appears on the branch that the universal appears on run through that quantifier. What I'm going to do in this session is first of all give you a couple of examples of trees. So I'm going to put some trees up here and work through them and show you how they operate. And then what we're going to do is we're going to turn to arguments, and we're going to apply the tree system to arguments, and I'll show you how to do a couple of trees for arguments. And then we're going to talk about a couple of further features of the trees. First of all, counter models, how to pull out models from a tree when the tree tells you that an argument is invalid. And then second of all, what to do when you hit an infinite tree. Okay, so let's get started by just doing a couple of trees in monadic predicate logic. All right, so first of all, I'm just going to put up some claims. All right, so here are three claims, and I'm just going to now use the tree rules to compute each of these claims. Remember that I introduced that thing called the order of operations. The order of operations here is something that I apply at every stage in the tree. So when I'm starting at this stage in the tree, I'm going to apply the order of operations to that stage, and then when I do something, I then reapply the very same order of operations. So that order of operations tells me to do propositional rules first, then negated quantifier rules, then unnegated quantifier rules, and then to return to the top of the tree. And to return to the top of that list of priorities. And with respect to the unnegated quantifier rules, I favor existentials over universals. Okay, so here's what this looks like. I look at this tree and first of all I go, are there any propositional logic rules to do? And I see that all of the rules that I've got here are quantifier rules of some kind. Next, I look to see if I've got any negated quantifier rules, and I see that all of the quantifier rules I have are unnegated quantifier rules. So I've got to deal with the unnegated quantifier rules. Next, I look to see if I've got any existential rules, because I do existentials before universals. And yes, I've got two different existential rules, so I'm going to have to do those first. So I'm going to start by doing those. First of all, I'm going to do this existential rule. I put in the first unused name, which in this case is lowercase a, to get out AA, and then it's done. Now I reapply that order of priorities. So I've done one stage of the tree, I'm at stage 2. Now I reapply that order of priorities and I go, okay, are there any propositional logic rules to do? Well, no new propositional logic rules have arisen, so I don't have any of those. Any negated quantifier rules? Well, no negated quantifier rules have arisen, so I don't have any of those. Any unnegated quantifier rules? Yes, I've got the existentials and universals, and so I've got to favor the existentials over the universals, and in particular, I now have to do this existential. So to do this existential, I'm going to plug in the first unused name, which in this case is B, and I'm going to get out AB and CB. Now again, I look at that order of priorities and I go, okay, are there any propositional logic rules to do? And what I can see now is that there is in fact a propositional logic rule. This conjunction down here, which was returned by the existential, is a propositional logic rule. So I've got to do that before I do anything else. Now I look at the tree again. Are there any propositional logic rules to do? No, I don't have any propositional logic rules. No negated quantifiers. Any unnegated quantifiers? Yes, I've got unnegated quantifiers. My existentials are all done, but I've still got this universal. So I've got the universal to do last. And in order to finish the tree, I've got to use that universal quantifier at least once, and then I've got to use it for every name that's arisen in the tree for that branch. So I look at that branch and I see that on that branch I've got two names, A and B, and so I'm going to run those through the quantifier. But what I'm going to do is I'm actually going to have to do them one at a time. So I start with the letter A, and I put that through the tree, and I get AA, arrow BA. And now that order of priorities kicks in again. Do I have propositional rules? Do I have negated quantifier rules and so on? And I've actually got a propositional rule that's arisen because of the universal, so I now favor that over doing the universal again. And I split that, I get not AA on one side and BA on the other side. That one thing that is still operating with respect to this tree system, just as it was in the propositional tree system, is that I'm constantly looking for closure. And because I've got AA here and not AA here, that branch closes. And I look to see if anything else closes, nothing else closes. And now what do I do next? Well, I don't have any propositional rules to do. I don't have any negated quantifier rules. The only unnegated quantifier rule I've got to do is this universal again, and I've got to finish it for the B in order to saturate the tree. So I run B through there again. I get A, B, arrow BB down here. And now I've got to do that conditional, and that conditional is going to branch. On one side, I'm going to get not AB, and on the other side, I'm going to get BB, and that not AB is going to close, and the BB is going to stay open. So now at this point, I look at my tree and I try and work out whether it's finished. Has every branch closed? No, because every branch hasn't closed. The other half of the completion rule is triggered. And I look to see whether I've applied a rule to everything that can have a rule applied to it. And I look to see I've done this, 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 and I've done this. So I've applied a rule to everything that can have a rule applied to it. And now have I applied a rule to the universals at least once? Well, yes, I've done the universal on this branch at least once. And now have I used the universal for every name that was raised in the tree? Yes, I have, because I've used it for the A and the B. And so at this point, the tree is finished. Now, it's important to note that I haven't tested an argument or anything like that. All I did was to just do a tree to just show you how the rules work. So we can't conclude anything about arguments from what I've done so far. In order to test an argument, we're going to have to take things a step further. So let's have a look at what that's going to be like now. So now if we want to test an argument, I'm going to put up a very simple argument. In fact, I'm going to put up an argument that we've seen previously. So at one point in the course, we actually translated out an English argument into something like this form. So we now have an opportunity to test this argument. When you're doing trees in propositional logic and you're testing arguments, the very first thing you do is negate the conclusion. When you're doing trees in monadic predicate logic, the very first thing you do is negate the conclusion. So you have to do that for any tree that when you're testing an argument, you always have to start by negating the conclusion. So we're going to drop a negation in there. And now we're going to run through our list of priorities to see what we have to do next. First of all, are there any propositional logic rules to do? We don't have any of those rules, so we can ignore that part of the priority list. Next, do we have any negated quantifier rules? We don't have any negated quantifier rules, so we can ignore that part of the list. Next, unnegated quantifier rules. We don't have any existential rules, but we do have a universal rule. So what we have to do is we have to do that universal rule. And now we have to use that universal at least once, and we have to use it for everything that appears in the tree. So what we're going to do is we're going to run A through the universal quantifier, because we've got that lowercase a appearing on the branch that the universal appears on. And then we're going to cache that out in order to get AA, arrow, BA. Now we look, are there any propositional rules to do? Yes, there's a propositional rule to do, and in this case it's the conditional, so we're going to do that. So that branches. On the one side we get not AA, and on the other side we get BA. Now we look to see if anything closes. The AA and the not AA close, and the BA and the not BA close. So what does that tell us about the argument? Well, just as in propositional logic, when every branch on a tree closes when you're testing an argument, that tells you that the argument is in fact valid. Let's have a look at another one. Okay. simple. PA, therefore, EX, PX. Okay, so that's my premise, PA, and I'm concluding EX, PX. So the first thing we do, as ever, is negate the conclusion. And now we're going to work through our list of priorities. Do we have any propositional rules to do? No, we don't have any of those. Do we have any negated quantifier rules to do? Yes, we've got a negated quantifier rule, so we're going to do that. So here we've got the negated existential rule. In order to operate on that, what we do is we turn the quantifier to the other type of quantifier and we move the negation over. So we turn that into for all x, not px. Okay, now we go through that list again. Any propositional rules? No. Any negated quantifier rules? No. Any unnegated quantifier rules? Yes. Any existentials? No. Do we have a universal? Yes, so we've got to do the universal next. In order to do the universal, we've got to run the universal at least once, and we've got to use it for every name that appears on the same branch as that universal. In this case, we've got an A appearing on the branch, so we're going to have to run A through the universal, and we're going to get not PA, and the PA and the not PA are going to close the tree. So this is another valid argument. Oops, that's not how you spell valid. Okay, got another valid argument. All right, let's do something a little bit more complicated. One thing that you can do in propositional logic is have multiple quantifiers operating, and this can be a little bit difficult to understand, so let's do one of those. Okay, so there's my argument. As before, we start by negating the conclusion. And now we look to see if there are any propositional rules to do. We've got this propositional rule here to do, so we're going to do that first. That's just the negated conjunction rule. And that gets us not AA on one side and not BA on the other side. Next, we look to see if we've got any we start that list again, we look to see if there's any propositional rules, we don't have any of those. Any negated quantifier rules, we don't have any of those. Any unnegated quantifier rules, well, we've got an existential and a universal. The existential takes precedence, so we do the existential first. Now we have to use the first unused name in the tree, and we're doing it up here. Now one of the important things to note is that when we do an existential above a branch like this, or above any number of branches, we then have to write what the existential spits out down on each of those branches. So I'm going to use the first unused name, which is going to be B, because I've got A appearing below that existential on the branch. Remember, the existential, the universal, they're always looking up and down that branch to see what names have been used, and the existential picks the first unused one up or down the branch, and the universal picks any name. So in this case, we're going to use B, and we're going to write down not PB. But importantly, we do it on both of these branches below the existential. And that applies to quantifiers generally. When you cache out the quantifier and you've got branches below the quantifier, you have to write the thing that you've dismantled the quantifier into on every open branch below that quantifier. Okay, now we go back to our list of priorities. Any propositional rules? No. Any negated quantifier rules? No. Any unnegated quantifiers? Yes. Any existentials? No, but we do have this universal, and now we've got two names, and we're going to have to run them through the universal ultimately to finish the tree, but we're going to have to do them one at a time. So first of all, we're going to do A, little a, to run that through the universal, and we write down below each branch A, Y, AA, arrow for all Y, PY. And just as with the existential, we wrote it down under each branch, we've got to do that here as well. Next, we're going to do these two, we look at our list of priorities again and we consider what we've got to do. Do we have any propositional rules? Well, both of these are propositional rules, so they are going to take precedence, so we're going to do them before we run the B back through this universal quantifier. So these are just conditionals. So they're fairly easy to handle. And I've done them both. Okay, so now we've done all our propositional rules. Now we look again to see if there are any propositional rules to do. We don't have any others, so we can ignore that list in that item in the list of priorities. We then look to see if we've got any negated quantifiers. We don't have any. Now we're back to unnegated quantifiers. No existentials, but now we've got universal here, and a universal here. When you've got multiple universals in your tree, you can pick whichever one you want to do. Now, at this point, an element of strategy enters into the picture. If I do this universal up here, this top universal, I'm going to get another 2 branches coming out of the tree, because I'm going to get I'm going to get 4 conditionals, 1 for each of those open branches, and then those 4 conditionals are each going to split. I'm going to end up with 8 open branches down the bottom here. That's fine, it's going to make the tree big, but it's not going to be wrong. Having big trees, though, can be a problem because they can become unwieldy and you're more likely to make a mistake. What you want to try and do is keep your tree as small and as simple as possible at each step. So if we have a look at this other universal, and we remember that we're allowed to run any name we want through universal, we're going to see if there's anything we can put through this second universal down here at these open branches that might actually help us to get some closure in the tree. Now if I have a look, these universals are each connecting to a py. So for all y, py is what both of those universals say. And I look above the branches of those that those universals lie on, and I notice I've got not pb on both branches. Now I'm allowed to take any name I want and run it through the universals. So what I'm going to do is I'm going to run b through that universal, which is going to get me pb, and that pb and that not pb are going to conflict, and that's going to close that branch. And I can do exactly the same thing over here. I get pb, I get not pb. Those are going to conflict, and that's going to close that branch. And so now, when I come back to this universal, which I do have to come back to, I'm not going to have to deal with 8 open branches. I'm only going to have to deal with 4 open branches. So that's sort of half the size that the tree was potentially going to grow to. Okay, so again, we go through that list of priorities. Any propositional rules to do? No. Any negated quantifier rules to do? No. Any unnegated quantifier rules to do? Yes. It's the universal, so I'm going to do that. Now, in order to finish the tree, I have to run every name that's been raised in the tree on the branch that the universal lies on and run it through that universal. Of course, I don't have to reuse these universals down here because those branches are closed. When a branch closes, you don't have to keep reusing the universal that appears on that branch. But these branches are open and this universal lies on both of those open branches, so I'm going to have to run that universal again. So that's what I'm going to do. I'm going to put the b through that universal, and that's going to get me ab arrow for all y, py on both of those branches down here. Now, I'm going to do the conditional rule because they're propositional rules to do, and the propositional rules take precedence. So I'm going to do those. And what's cool is I can now do that same trick that I did with the universals over here to this universal that appears on these open branches down below here. So I can take B and I can run it through this universal to get PB, and that's going to close that branch. Take B, run it through that universal to get PB, and that's going to close that branch. All right, now I look to my tree to see if there's anything else I can do. I've applied a rule to everything that can have a rule applied to it. I've got 2 open branches, and I've saturated the tree by using the universal for every name that's been raised in the tree. So this tree is finished. So we can now talk about what this is going to imply for the argument. So the tree's finished, and we've got at least 1 open branch. Now what that immediately tells us is that the argument is invalid, so we can grab that piece of information straight away. But what we need to work out now is what a model or a counterexample to this particular argument is going to look like. We have to talk about how it is that you draw out that information. So that's what we're going to do next. So we've got these 2 open branches. I'm just going to number them so you can tell. We've got number 1 here and number 2 here. Now, just as in propositional logic, every open branch corresponds to a counterexample, so too do both of these open branches correspond to counterexamples. In monadic predicate logic, a counterexample is a model. So when we're building a counterexample, we're producing some model. And what the model does is it's a model where the premises are true and the conclusion false. So that's what we're going to try and do, is we're going to try and build a model now based on our open branches, under which the premises are true and the conclusion false. Now the way that we do this, the very first thing that we do is we pick one open branch to work from. I'm going to work from this leftmost open branch. And what we do is we read off the information that we have available to us on that open branch. So I look at that open branch, and by information, what I'm interested in are the values for the basic propositions or the negations that appear on that branch. So if I look up this branch, I'm going to look to see what kind of information I have. Well, I've got not AB, which is there. Look up the branch a little bit. I've got not AA, which is there. Look up the branch a little bit more. I've got not PB, which is there. And I've got not AA as well. Okay, so I've got those 4 pieces of information. And so I'm going to write those 4 pieces of information down just to keep track. And I'm going to write it down like this. I know that because I've got not AA, I know that AA is false. I know that PB is false because I've got not PB. I know that AA is false, but I already knew that. I'll just write it down. Actually, I won't write down redundant pieces of information. So only write down unique pieces of information. And then I've got AB is false. All right, what we're going to do now is we're going to take that information and we're going to use it to build a model. Now remember what a model has. A model has 3 things. It has a domain of objects. It has an extension for each of the predicates that you're dealing with, and then it has objects assigned to names. Now, if we look at the sentences that we've got, our model for these sentences is going to have to set a domain of objects for those sentences. It's going to have to set an extension for the 2 predicates A and P, and it's going to have to assign an object to the name A, the lowercase a, because those are the things that appear inside the tree. So, a good rule of thumb to get started with building models is you start with a domain. You start with a domain of as few objects as you can get away with. So in this case, I'm just going to start with 1 object. If I need to add more objects, I'll see that as I go through. But if I can get away with just having 1 object, then I want to sort of keep my model as small as possible so it's the easiest as possible to work with. All right, now what I've got to do is I've got to set extensions for A and P based on that domain of objects, which is just 1 object. So in this case, I've got to set the extensions so that I get this information out here being true, right? So that means I have to set the extension of A in such a way that lowercase a is not in the extension of A. So first of all, before I set the extensions then, I'm going to have to assign A to an object. So I'm going to say that A is equal to 1. It picks out this 1 object that I've got inside my domain. Remember, names have to pick out something, so you have to have everything that appears, every name that appears inside your model picking out some object. So I've got to assign it to something. I can't have an empty name. All right, next, I'm going to set the extensions of A and P so that it gets this information out. Now, what is the information I want? Well, I want it to be the case that whatever lowercase a picks out is not in the extension of A, and whatever lowercase b picks out is not in the extension of P. So I need to also make sure that I set lowercase b to be something as well. Now notice that I've set A and B to the same thing. You're allowed to do that. You're allowed to have multiple names pick out the same object. What you can't have is the same name picking out multiple objects. So in this case, I've got multiple names picking out the same object. That's fine. All right. Now I want to make it the case that whatever lowercase a picks out is not in the extension of A, because then AA is going to be false. I want whatever lowercase b picks out to not be in the extension of P, because then PB is going to be false. And I want whatever lowercase b picks out to not be in the extension of A, because then AB will be false. And that's replicating this information that I've got on this open branch. So the easiest way to do this is actually to just empty the extensions of both A and P. So in this case, what I've just done is I've set the extension of A and the extension of P to be the empty set, which is to say I'm saying there's nothing in the extension. They're like the predicate is a unicorn in that they don't apply to anything whatsoever. What that does is it automatically makes it the case that AA is false, lowercase a is not inside the extension of A because nothing is, and lowercase b is not inside the extension of A because nothing is, and lowercase b is not inside the extension of P because nothing is. All right, so this model that I've just built here captures this information on this open branch. All right, so what I've done is I've taken an open branch, I've read off this information, and then I've built a model which was able to yield that information there, to be able to satisfy the constraints laid down by that information. In particular, I've set the extensions of A and P so that AA and PB and AB are all false, and I've assigned objects to A and B from the domain so that we can calculate these values up here. Now what I've got to do is I've got to test to see whether this model is one that does in fact make the premises true and the conclusion false. Now in order to do that, I'm going to go through each of my premises and my conclusion and evaluate them against this model to see if they're true or false. Now remember, the conclusion is the thing without the negation. We added the negation in order to test the argument, but the argument itself didn't have that negation in there. So what we're actually trying to work out is whether the conjunction AA and BA is true or false. So one thing that we've got to do immediately is actually add in some extension for the predicate B. Although we set the extensions for A and P, you've got to make sure that every component of your argument actually has some extensions set for it inside the model. Otherwise, the model is not a model for the argument. The model has to reflect all of the moving parts of the argument, and so we've got to set some extension for B. But notice that this information that we read off this branch didn't really give us any constraints, didn't tell us anything about B. What that means is that we can actually set the extension of B to whatever we want. It doesn't matter for the purposes of this argument. So the easiest thing to do is to just set it to be empty, like the extensions of A and P. All right, so now we've got a model that we can actually test against this argument because all of the features of this argument are reflected in the model. Okay, so we're going to start with the conclusion. Is it the case that AA and BA is false, which is what we want? We look, for this to be false, either little a has to fail to be in the extension of big A, or little a has to fail to be in the extension of big B, or both. And in fact, both of those things are true. Little a is not in the extension of A, and little a is not in the extension of B, because nothing is in the extension of either of them. So this conjunction is false. So the conclusion is in fact false. So that's a good start. This model makes the conclusion false, and we want this model to make the premises true and the conclusion false. Next, this second premise. This says, this second premise should have a Y there. Oops, that's not good. I just managed to delete the entire argument. Okay, so let me just build a model, and I'll rewrite the argument after. I should be able to redo the model without the tree. So the argument was, for all x, if ax, then there's some y such that, for all y, py, and there is some y such that not py, and then the conclusion was AA and BA, and our model was, we had domain of one object A, B, and P, all had nothing in them, and then A equaled 1 and B equaled 1. Okay, and this model was supposed to be a model under which the premises are true and the conclusion false, and that's what we're trying to test. So we look to see whether it makes the conclusion false, and we already concluded that it does. Makes the conclusion false because in order for it to be false, either AA has to be false or BA has to be false, and in fact both of those are false because the extensions of both of those predicates are empty. So we know that the conclusion is false, which is what we want. Next, we want to see whether this second premise is true. There is something that's not in the extension of P. In this case, we know that there's something that's not in the extension of P because everything fails to be in the extension of P because P is empty. So we know that this second premise is true. And then the last thing we have to deal with is this top premise, namely for all x, if ax, then for all y, py. Now, in order to test this, what we're going to do is we're going to do the slow and methodical thing that we learnt about when we were doing models, and we're going to test the model for every value of x. And the reason that I kept the model as small as possible is because when you're actually testing this proposition using the model, you want as few cases to have to work through in order to work out whether the premises are true and the conclusion false. So because there's only one object in the model, I only have to test x equals 1, and I have to plug that through this statement in order to see whether or not it's true or false. Okay, so first of all, I set x equal 1, and that's going to get me a 1, and then for all y, py. And now, I don't actually need to go any further because I've already got the answer to whether or not this proposition is true or false given this model. If I look here, what I'm testing to see is whether 1 is in the extension of a, because that's what I've set x to. 1 is not in the extension of a, so I know that the antecedent of this conditional, the thing on the left-hand side, is false, which makes the conditional automatically true regardless of what's going on the right-hand side. Because there's only one value of x to test, we know that this universal is true for all values of x, and so that we know that this conditional is true for all values of x, and that's enough to make it true that the premises, that first premise is true. So this model that we've built is in fact a model under which the premises are true and the conclusion is false. And because it is in fact a model under which the premises are true and the conclusion false, and it's something that we read off that open branch of the tree that we did, then what we've been able to do is take an argument, show that it's invalid, and then pull out a counter model, a case in which the argument falls down, and then demonstrate that that counter model is in fact a counter model to the argument in question. All right, let's do another one. I'll make this one a little bit shorter so that we can focus on the invalid, the sort of notion of an invalid argument and on building a counter model and then testing that counter model. So let's have a look at a somewhat simpler argument. Okay, so have a look at that argument. Now we're going to test this argument. In order to test this argument, we start by negating the conclusion, and then we look to see what rules to do next. We don't have any propositional rules or unnegated quantifier rules. All we've got is this universal quantifier rule. And in order to complete the tree, we have to use this universal quantifier at least once, and we have to use it for every name that's been raised in the tree. So what we're going to do is we're going to take A, we're going to run that through the quantifier to get A arrow BA. And now we look to see if there are any propositional rules we can do. There is in fact a propositional rule to do, namely this conditional, so we're going to do that. Okay, now, does anything close? Well, on this branch we've got not AA, and BA, so none of that conflicts, so that's fine. Over here we've got BA, not AA, and BA. None of that conflicts, so that's fine. So none of the branches close. We've used the universal for every name that's been raised in the tree, and we've done everything, we've applied a rule to everything that can have a rule applied to it, and we've used the universal once, so we've saturated the tree. So the tree is finished and it's stayed open. So what that tells you is that the argument is invalid. Now what we're going to do is we're going to pull out a counter model from the argument. We've got two open branches. We can use either of those to pull out a counter model, but ultimately, as you can see, we've sort of got the same information on both branches, so it doesn't really matter which branch we use in this case. Okay, so let's just pick branch 1, and we're going to use that to pull out the information. We start by seeing what information we've got on that branch. We've got that AA is false. We've got that AA is false. We already had that, so we don't write down a redundant piece of information. And we've got that BA is true. So that's the foundation for our model. Now what we have to do is build a model that reflects that information, and then using that model, we test to see whether it makes the premises true and the conclusion false. So as before, we're going to start with the smallest domain we can get away with, namely one object, and then we're going to set the extensions of our predicates in such a way that makes the premises, that makes this information come out to be true. So we're going to have an extension for A, an extension for B, and we're going to assign an object to lowercase a. Because we've only got one thing in the domain, we've only got one thing that we can assign A to, so we're going to assign A to the object 1, and then we're going to set the extensions for these two predicates. Now what's important is that we try and capture this information. We know that BA is true, which means that whatever A picks out is in fact inside the extension of B. So that means that we have to put the number 1 inside the extension of B on this model. We know that lowercase a is false and we know nothing else. So we know that that lowercase a is not inside the extension of a. So because we don't have any further information and we know that it's false for lowercase a, we can just empty out the extension of a, and that's going to make this true. Lowercase a is not in the extension of a because nothing is, which is going to make a false. All right, so there's our model. It's a very simple model. Now we're going to test to see whether this model makes the premises true and the conclusion false. Remember, the conclusion is the thing without the negation. We added the negation to test the argument. So we're going to try to see whether AA is true, BA is true, and then for all x, AX, arrow BX is true. So we start with AA. Is AA true? Well, no, because we've set the extension of A to be empty, so nothing is in the extension of A, so little a can't be in the extension of A, so that gives us what we want, namely that the conclusion is in fact false. Next we try to see whether BA is true, whether the thing that lowercase a picks out is in fact inside the extension of B, and we can see that it is because we built that into the model, and so we know that BA is true. Finally, we've got for all x, if AX then BX, and we've got to test that. We can test that as before in the slow methodical way. What we do is we set x to be the number 1. We've got to try every value of x that we've got in our domain. We've only got one possible value for x in our domain of objects. So we're going to set x to be 1, and we're going to run that through this argument up the top. If we run that through this argument up the top, this proposition up the top, we're going to get A1 arrow B1. And that claim there that conditional claim is true because 1 is not inside the extension of A because nothing is. And because 1 is not inside the extension of A, this conditional comes out true. It's true for all values of x because there is only one value of x, and so the universal quantifier is true, and so this entire proposition is true. And so there we have a demonstration that this model that we've built is in fact a model under which the premises are true and the conclusion is false. Now, one thing to keep in mind is that this isn't the only model. There could be many, many different models. You could just take this model and add a bunch of objects into the domain and you would be able to produce another model that makes the premises true and the conclusion false. So there are lots of ways to make models that reflect the invalidity of an argument, but not every model that there is for an argument is represented inside the tree that you've produced. So this tree really just sort of points us towards this particular model, but there are lots of models that could actually do the same work. And you can work this out by just sitting there building models at random and testing them in the way that we just tested this model against the argument that we started with. Okay, so that gives you a sense of how to actually apply the rules that we've learned from monadic predicate logic to arguments inside the language. And it shows you how we can test for validity and invalidity in much the same way that we did in propositional logic. And we can draw out these counterexamples which allow us to build models that reflect the situation in which the premises are true and the conclusion is false. What we need to do is have a look at one last thing in order to finish off our understanding of the monadic predicate logic trees. Once I'll go through this basic notion of an infinite tree, and then we'll do another example to see how this all works. So consider the following argument. I'll write it up big for you so you can see it. For all x, there's some y such that px and qy. Therefore, for all x, qx. That's my argument. Now what I'm going to do is I'm going to test this argument, and we're going to see what happens when I try and test this argument. Okay? So for all x, there's some y such that px and qy. Is that right? Yep. Therefore, for all x, qx. Okay, so that's our argument. Now what we're going to do is we're going to test this argument in just the same way that we tested the last two arguments. We're going to negate the conclusion first. So we throw that negation on. And now we go to our list of priorities. We consider what do we need to do first. We look to see are there any propositional rules in the tree. Well, there aren't any propositional rules because all we've got are this unnegated quantifier rule and this negated quantifier rule. Next, we look to see if there are any negated quantifier rules. Well, there is a negated quantifier rule, namely this one just here. So we're going to do that next. The negated quantifier rule tells us to flip the quantifier into the other kind and move the negation over. Next, we look to see, we go back to our list of priorities. Do we have any propositional rules? No. Any unnegated quantifier rules? No. Any negated quantifier rules? No. Any unnegated quantifier rules? Yes. We've got a universal sitting here and an existential sitting here, and we've got to try and do one of these. The existential takes precedence, so we're going to do that one first. So we don't have any names in the tree yet, so we can use lowercase a as our first unused name. So we're going to add that into the tree to get not QA. Now, we do the universal claim. That's the only thing we've got left to do. So we're going to run the lowercase a through that universal. We've got to use that universal at least once. We've got to use it for every name that's been raised in the tree. The lowercase a is the only name that's been raised in the tree, so that's what we're going to use. We run that through and we get EY bracket PA and QY. Remember, you only remove the variable that's bound to the quantifier when you're doing the rule. So because the x is bound to the x, in the universal and the existential is binding the y, we get rid of the x when we get rid of the universal, but we leave the y and the existential intact. So now we look to see what we've got left to do in the tree, and we've got this existential that's been raised in the tree, so we're going to have to do that next. We look up in our tree, we see what names we've got. We've already got A, so we're going to have to use the first unused name, and that first unused name is going to be lowercase b, and we're going to get PA and QB. Okay. And now we do the conjunction that we've got here, because that's a propositional rule and it takes precedence. And then we look to see if the tree is finished. Now remember, when is a tree finished? A tree is finished either when every branch closes or when the tree is saturated. Now in order to saturate a tree, we have to take the universal and use it for every name that's been raised in the tree. We've used it for lowercase a, but we haven't used it for lowercase b. So in order to saturate the tree, we've got to take that lowercase b that appears here and run it back through the tree in order to finish it. So let's do that. So I do that, and remember, we just get rid of the x, because the x is bound to the universal quantifier, not the y. We end up with EY, PB, and QY. All right, well, now we look at the tree. Are we finished yet? Well, no, because this existential that was in the scope of the universal has now come back to haunt us, and we're going to have to do that again before we can finish the tree, because saturation requires that everything that can have a rule applied to it does have a rule applied to it. So let's do that. We take this, we've got A and B already appearing in the tree. We've got to use the first unused name. In this case, that's going to be C. So we're going to put C in, and we're going to get PB and QC. And that's going to give us a conjunction to deal with, and the conjunction just gives us PB, QC. Is the tree finished? Well, in order to saturate the tree, I've got to take every name that's been raised in the tree and run it back through the universal. But we just had a new name get raised by that new existential that we just produced. So we've got to take that name and now run it back through the universal. If we do that, then we end up with EY, PC, and QY. Are we done yet? Well, no, because I've got this existential to do, and in order to finish the tree, I've got to use every rule that can have a rule, every proposition that can have a rule applied to it. I've got to apply a rule to that proposition. So I've got to apply something to this existential. We've already got A, B, and C in the tree, and now I have to add a new name, and that new name is going to be D. So I add D in, I get PC and QD. I do that conjunction, just continue that over here, I get PC, QD. Are we finished yet? Well, no, because now I have to take that D and run it back through that universal. And hopefully you can see what's going to happen. Every time I take a name and run it through this universal, I get a new name being called by the existential that's sitting inside that universal scope. And when that existential calls that new name, I've got to take that new name and run it back through the universal. But every time I do that, I've got to then raise a new existential and get a new name and run that back through the universal, and so on ad infinitum. What's going to happen is that this tree will go on forever. There is no way to complete the tree in the sense that the last two trees were completed. We can't saturate the tree in a finite number of steps. What's interesting is that the tree does get saturated in an infinite number of steps. If I could continue to do this tree forever, then the tree would in fact be saturated. But because I cannot do that, I've got to make a judgment call here about what to do with the tree. And the judgment call I make is basically this. When I see a tree starting to do this, and I see a pattern starting to repeat, then I stop at one of the repetitions of the pattern. So if you look at the tree, there is a definite pattern. When I got here, and when I did that, right, so you look at what's above this blue line, and then between that blue line and the next blue line, you can see that you've got the same thing recurring over and over again. You get this repetition happening inside the tree. And so what you have to do in order to finish these infinite trees is you take them to this point of recursion when they're actually repeating the pattern. And the pattern can be quite complex. This is a fairly simple pattern, but you can have a very complicated pattern. And so it can take a while to hit the point where you've actually started to repeat the pattern. But what you do is you make sure you repeat the pattern at least once. So you hit at least one iteration of the pattern, and then you stop. You determine that the tree is infinite, it's going to go on forever, and then you let the tree go at that point. It's sort of a little bit of an unsatisfying rule to have. Previously, our completion rules for the tree have been very principled. They've been things like use every proposition that can have a rule applied to it, and use the universals at least once, and use the universals for every name that's appeared in the tree, and that was all very good and rigorous and precise. And then when you get here, it's sort of like, well, just keep going until you just don't want to go anymore because it's doing the same thing over and over again. Unfortunately, we don't have a more principled thing to say. There are sort of more principled things you can prove and understand if you start to think about infinitary languages and the structure of infinite systems and all that kind of stuff. We don't really want to have to go there. For our purposes, it's enough just to see the repetition of the pattern. Okay, now at this point, an important question arises. If I see this kind of repetition, what should I conclude about the argument? After all, this was an argument that I started with. Well, we know that the tree is never going to close. And it's partly definitional of a tree being infinite that at least one of those branches stays open. It stays open forever. There's nothing you can ever do to close the tree. So what we know immediately, whenever you've got an infinite tree, as soon as a tree is infinite, you know that the argument is invalid. So you have that piece of information straight off the bat. Now, the question at this point is, how do you build a model for this kind of tree? What you do is you take one of these lines of recursion, one of these points where the tree has started to repeat itself after at least one iteration. So here's the first iteration, and here's the second, and here's the third. You take it at least to the point of one iteration, and then you draw a line and you build you read the information from that iteration up, and you build the model from that point. So there's an infinite number of points that you can build the model from. The easiest point is to build it from the point of the first iteration, but you can build it from the second or the third or the fourth point of iteration. I'm going to build it from the second point of iteration, so I'm going to build it from here. And what I do is I draw that line there, I ignore everything below the line, and I read the information up the tree as if this were the open branch in a finite tree, one of the other trees that I've done. And then I use that information to build the model. So what information do I have reading up that part of the tree from that line that I've drawn at the end of that second recursion? Well, what I've got is that QC is true. I've got PB is true. I've got QB is true. And I've got PA is true. And then the last thing I've got is that QA is false. All right, so I've got those 5 pieces of information. If I took it to a third point of recursion and I read the information there, I'd have more information to read. So the deeper you go with your tree when you're reading the model off, the more information you're going to have, but you don't get any advantages to having more information. You should be able to build a perfectly adequate model from any of these points of recursion. So it stands to reason you should sort of make the job as easy for yourself as possible by taking one of the fairly low cardinalities of recursion in this situation. Okay, So I've got this information. Now I'm going to build the model just as I did in the previous case. So I'm going to start with my domain of objects. Now in this case, what I'm going to do is I'm going to start with 2 objects in my domain. Why am I going to start with 2 objects? Well, I can see that there's something that's inside the extension of Q, and there's something that's not inside the extension of Q, namely lowercase a, and there's something that is inside the extension of Q, namely lowercase c. So that's going to tell me that there is at least 2 things here. The very same thing can't be both in and outside the extension of Q, and because of that, because I know that there's something outside the extension of Q and I know there's something inside the extension of Q, I'm going to have to make sure there's at least 2 objects to reflect that fact. So I'm going to put 1 and 2 in. And now I'm going to set the extensions for Q and P. Sorry, first of all I'm going to name those objects using A and B and C. What I've done is I've set B and C to be the same object, but I've set A to be the number 1. You're allowed to do that. You're allowed to set, as I said before, multiple names to the same object. What you can't do is set one name to multiple objects. And so now what I'm going to do is I'm going to set the extensions for my predicates. So I'm going to say that P is such that PA and PB are both true. So I need to put 1 and 2 inside the extension of P. Right, which gets me this piece of information and that piece of information. And then I need to set the extension of Q. And I need to set it so that A is not inside the extension of Q, but C is. And so I put 2 inside the extension of Q, which gets me that QC is true, but QA is false. And then I also need it to be the case that the thing that B names is inside the extension of Q, but because B and C name the same thing, I've already done that by putting the thing that C names inside the extension of Q. So there's my model. Now what I've got to do is I've got to test the model, but before I do that, it's worth pointing out that the model here is finite. There's a finite number of objects inside the domain. I've only got 2 things. I don't have an infinite number of things inside the domain. You can have an infinite number of things inside the domain, so you can have a model that's infinite. This is not an infinite model, and not every infinite tree has an infinite model. In fact, most infinite trees are going to have at least one finite model, and it's usually easier to find the finite model and draw that out rather than trying to write out an infinite model. Okay, so I pulled a finite model from an infinite tree, and I did that by stopping at one of these lines of recursion and reading the information off the tree. So now I'm going to test to see whether this is in fact a model that makes the premises true and the conclusion false. So remember, the conclusion I'm looking at is the thing without the negation. So I want to see if for all x, qx is false. Now in order for that to be true, everything inside the domain would have to be inside the extension of Q. Only one of the things inside the domain is inside the extension of Q, and so I can conclude that for all x, qx is in fact false. So I've got that right. So the model does in fact make the conclusion false. Next, I want to see whether the first premise is true. And what the first premise says is for all x, there's some y such that px and qy. So what I need for this first premise to be true is for it to be the case that everything is inside the extension of P and something is inside the extension of Q. That's basically what that first sentence says. So I look to see, is everything inside the extension of P? Well, everything in the domain is inside the extension of P because the domain and P overlap completely. So this first part here is true. And there's something inside the extension of Q because 2 is inside the extension of Q. So I know that that side's true, so I know that the conjunction is true. And I know that this is true for all values of x, and this is true for some value of y. No matter what I put in for x, px is going to be true, and there's some value for y that I can put in for q that's going to make qy true. So some value of y some value for y that I can put in that's going to make qy true, namely if I put in the number 2. So this is a case where the premise is true and the conclusion false. Okay? So this is a difficult case. What we've got is an argument that produces a tree where the tree itself is infinite, it goes on forever. But even when you've got an infinite tree, as long as you halt at one of the points of recursion and read the information off the tree going backwards, you can use that information, draw it out, and then use that to build a model, and then test the model, and you can end up with a finite model that makes the premises true and the conclusion false. Interesting question as to whether there's an infinite model that does the same thing. Interesting question as to whether there's ever any set of sentences that requires a model to be infinite or requires a model to be finite. Those are difficult questions, and I will leave you to ponder them. Until next time, get some practice doing these trees. In particular, take an entire argument, make sure you test the argument using the tree. If it's invalid, build the model and then retest the model. That's going to give you practice in translating English into the predicate logic. It'll give you practice in doing the monadic predicate tree rules. It'll give you practice in building models, and it'll also give you practice in testing propositions against models. All right, thank you.